Welcome to lecture 29 of MCS 471, so scheduled for 29 October. We are today looking into higher order equations. So we introduced ordinary differential equations and initial value problems in the last lecture. Then we had the standard format that we looked at first order differential equations. What we will see now in this lecture is that every higher order equation can be reduced to a system of first order equations. We will see again the application of Euler's method and the modified Euler method, but now on a system of first order differential equations. As far as the systems go, we distinguish between linear systems and nonlinear systems. So for the linear systems, we have a very good and a very nice complete solution if we look at the eigenvalues and eigenvectors. So that is the spectral decomposition. For nonlinear systems, things are starting to get a lot harder, and there we essentially have to rely on simulations and our skills of numerical analysis. So last lecture we ended rather with some discouraging statements. We no longer have a backward error to go back to, so we are solving equations, but unlike in the beginning of the course where we could always plug in our solutions into an equation, this no longer works now because we have points that approximate a function to an equation. On the other hand, I mean, there are plenty of examples and test properties. In all the examples we consider today, the periodicity matters a lot. So we are considering phenomena that have a periodic solution. So checking whether your numerical solution then also is periodic is a basic test we will do. So we will consider two main applications, or I would actually call them benchmark problems, the pendulum, swinging pendulum, and a very simple model of a predator-prey simulation. And the main part again is that to show the application of the modified Euler method, a method that we derived last time. All right. Here we have a higher order equation. So the order of the equation is n. So we have an nth order. So the equation is already monic. So monic, this means that the leading coefficient is 1. So it's an honestly good equation. So we have a general notation of the derivatives. So you notice the powers, which are actually the superscripts, which are not powers. We put them between brackets, between these round brackets. All right, so we are looking for functions. Our higher order differential equations will still here be linear, in the sense that the coefficients are independent of x and y. So x is the independent variable. An alternative letter is t for time, and y depends on x. All right, so this is a higher order equation in standard format, where the format is determined by the constant coefficients, the a's, and the function of two variables. Here is an example. So we looked at this example last time, but now the right-hand side is extremely simple. We have 0, but this is a second-order equation. So with the first-order equation is if the right-hand side is constant, and actually you have a linear function. But now we have a second-order equation, and the solution will be periodic. It will be a linear combination of cosine and sine functions. And indeed, we can verify that if we take derivatives of this linear equation, then we see indeed that the second plus the linear combination equals 0. In a fine textbook example. And here we already see the periodic nature of the solutions coming in. And that will help us. We can rewrite every general higher order differential equation into a system of first order equations. I will illustrate this for order 3. If you can do it for 3, you can do it for any dimension. So what is the trick? The trick is to work with auxiliary variables. So we have new variables that we introduce. So we have an order 3. We will have 3 variables. So the original y, we will label this y1. Its first derivative, that will be y1 prime. The second derivative will be will be y2, and the third derivative is y3. So with this notation, we can then derive the equation. And now I see that there is an embarrassing bug in. So this should have been a 1 here, and this should have been a 2. So let me fix this. So because we have that the y3, which is y2, so here it is correct. We then can replace the original equation into a first order differential equation. So in standard form here, we have that the first order, the derivative of y3 is a function of x and y. So the f is now a little bit extended. We subtract the combination. All right, we have one equation, that's the first order, but we have now 3 variables. Well, how do we turn this into a system? We remember the definitions. So we remember that we have that y1 is the derivative of the original equation. And actually here it is again wrong. I'm sorry. So there are a lot of typos on the slide. So if we have that y, oh, okay. So here, no, it's still wrong. So y1 is the original equation. So this would actually be y1. Then here we have y2, and here we have y3. Because you see that the equation that we have here, that I now just underlined, is y1 prime equals y2. So the symbols that we introduced, the relations can be written in the standard format. So the left-hand side is always a derivative. The right-hand side is always the underivative, the variable, the original variables. So the punchline of the slide is that a third order differential equations becomes a system of three first order differential equations. And there is a standard way to rewrite the system. Here it is again. So this is summarizing. We rewrite the equation and we write it more in a standard form. So not that the third equation comes first, the third equation now comes last. And as usual, when we have linear systems, so this is a linear system now, we write it in matrix vector notation. All right, so this is a definition of, this is our first example of a linear system, where in general we will have y prime equals a times y plus some function. All right, let's see how we can now apply Euler's method to it. How does Euler method work again? Well, we have our standard formulation. So this is Euler's method for one variable problem. So we have the standard formulation. We compute approximations on some mesh. So we have still only one independent variable. It's called x, but it will be called t later on, and we still work with a fixed step size. So we have Euler's method, which I'm now boxing in. Euler's method is then naturally generalized in vector notation. So we have, suppose we have three dimensions. We have 1, 2, 3 as the second index, 1, 2, 3 for the approximations. So our approximations are now starting at these values here. And our function, our little f, is actually now a fat f of three functions, f1, f2, f3. So in pure notation, we see that the method of Euler immediately generalizes to systems. So this actually implies that we can solve any higher order equation. And let's do this. Let's look at an example or an application. So we consider a pendulum, that means some weight hanging from a string with length L. That's the length of the pendulum. We have the mass of the pendulum, and then we have the gravitational constant. So the pendulum is subject to gravity. So we have here two pictures on this slide. At the left, you see the pendulum at rest. Nothing is moving. At the right, we have an initial deviation from the equilibrium point. I say the equilibrium point. If the string is a fixed rod, then there is also another equilibrium point, but that's an unstable one when the angle is pi. So to be, if the it's not a string but a bar, a fixed bar, then actually you have two equilibria. But let's here assume that we will never make any more deviations than 45 degrees. So as a pendulum, you could also consider a swing. All right, so what is here, what are we after? We are after for the evolution of the angle that the pendulum makes with respect to the equilibrium. So we can give an initial position and then a zero velocity. So think about pushing a child on a swing. you give it an inclination of 45 degrees, and then you let go, and gravity will do its work. How do we get to equations? Well, we need some physics for that. We have the laws of motion, so Newton again, but now Newton from physics, and you see that differential equations come in extremely naturally. We have that the forces, so the second law of motion says that the force is proportional to mass times acceleration. So acceleration is the second derivative. So that's where the second derivative comes in. So this force, we have the gravitational force, and the gravitational force has a component so the gravitational force is the red arrow. Then we have the blue arrow that essentially is used in the right-hand side of our second order differential equation. All right, I'm probably not explaining this quite well. Physics is not my strong suit. But we have a differential equation, and we can see that the mass, the m, essentially in our simulation will not matter. So that's the first thing we can simplify already. So the m we strike out, and we can make this also dimensionless by having unit length for the string. That gives us then immediately a simpler problem. So here is our simpler problem, or we could say that the G over L is our constant. So we have a second order differential equation that we rewrite as a system of two first order equations. So we can do that again from scratch. So there were some notational hiccups. Let's see if we can recover from this. So we have y1 is the original variable, y2 is its derivative. Then the second derivative is y1 is y2 prime. Okay, so that's important here. So y2 prime is now written, so the second order derivative of our original problem, of our original function, is now rewritten as a first order differential equation. So we have two equations here on this slide, two differential equations at the two first order ones. We have the relationship between y1 and y2. So y2 is the derivative of y1, and we write this in the standard form. Derivatives come to the left, and then we have our original problem. All right, it's ready now for application of Euler's method. So we apply Euler's method to this problem, which is, we have two variables, y1, y2, and we are going to compute approximations for the deviation that the pendulum makes by application, by stepping forward in time. The next approximation is the current one plus h times the function value. So it's very important now that we see that the function value, so the function value here is this right-hand side. So this is the fat f, the vector function f, in function of x, or actually time here, I think it was time. So time t, y1 and y2. So this has two components. So it's important not to mess up with the indexing. So you see here we have a y2, so the first function component. So the function that will give the first coordinate will actually be copying the second component. And then the second value, the f2 and the f, will actually use the y1. So it's very important not to get the indexing wrong. So y2 and y1. So the code for this is extremely short, but there are some subtleties. So we will start with the pendulum that has no velocity. So that's also important. What is now the y1 and the y2? The y1 is the position, the y2 is the velocity. We take dimensionless, so we have unit length for the string. All right, so let's do this. One simple function that has two parameters. This is a periodic function. So we are returning a range of time, a range for positions, and a range for velocities. So the two important parameters are the number of steps that we take, and also there is a natural periodicity coming in here. So we are essentially determining how many cycles that we want to see for this problem. So this is a very basic module of a pendulum. I should say that this problem has no symbolic solution. So if you are solving this symbolically, then typically what people do is they assume they replace the sign here. The sign for small angles is actually equal to its argument. So if you want the symbolic solution, then one uses a Taylor series of the sine function. So just to say here, this is a very simple problem, but numerical analysis is already quite useful. All right, but very difficult as well. Numerical analysis is difficult because we did not make any mistakes in the code. Observe here the application of Euler, the attention to the indices. So the y1 and the y2 here, which are flipped. So this is a simple tuple assignment that evaluates the sine function in every step. So this is logically a correct program, but if we make the plot, so we wanted 3 cycles and no more than 100 steps here per cycle, then it actually goes quite wrong. So the position of our pendulum, and note that the position is expressed as an angle. So, and the angle is in radians. So you can see that after step 5, well, step 5 is probably still correct, but we have nonsense coming out here. So, with a correct program, and in a way, the explanation is that Euler's method is simply a method that is too simple. Even for simple problems. Let's see how we can fix this. Here is the corrected picture. We have the position and the velocity. I said 3 cycles, but you see that it actually runs a lot faster. So we have, but it is a quite plausible and correct model. We see that our pendulum, it starts at 45 degrees and there is no friction, so we will never exceed the 45 degrees. So the blue position will not go out band. It will stay within the 45 degrees. And also it's interesting to look at the velocity. We start at 0, and also the velocity somehow peaks at some point. So the velocity is a vector here. It has an orientation, whether we go in the negative direction with our angle. So we start at pi/4 and we decrease it, so that what the negative velocity means. And then it starts to increase. So before, you can see that the values of the velocity have to come before the values of the position. And the same for the peaks of the velocity, they kind of come before the peaks of the position. So this picture looks correct. So that's kind of the justification, the qualitative validation for the model. Okay, how does the modified Euler method work again? Well, the modified Euler method is a predictor-corrector method. We use the Euler method. So we have the system here, and we have the prediction. So this is the predict the P stage, and then we have the correct stage. So the modified Euler method is important representative for an entire class of methods, where we have a low order method. So the Euler method is actually not completely useless. It helps to improve the modified Euler method, which is actually an implicit method. So why did we need this? Well, observe the bars. So the y1 bar here is used over here. So notice again in our equation here, the 1, so the correct application of the indices. The y2 is then used. I won't make a complete mess of the slide, but please look very carefully at the indexing on how the methods are applied. So in a way, we do a weighted, in the correction stage, we do a weighted evaluation of the function evaluations. So we have the format of the trapezoidal rule again. Here is the code. It's a little bit more complicated, but everything fits on slide. We first compute all the values, and then we store everything in 3 arrays for plotting. All right, our first example. Here we let it run, and we check the periodicity. So I print both the Euler method and the modified Euler method. The last column, so we have the index for the step, then we have the values for time, so, and then the predicted and the corrected value. At the end, there is the error. And one can see that the Euler method is quite bad. The error starts to get very large, but the modified Euler method actually produces still a very nice picture. So the 10 to the power minus 2 at the end is not accurate, but it's quite good enough for the picture. We don't see the difference in the pictures. All right, our first model is actually not really a realistic model. So if you have a child on a swing, you will realize if there is no push, then the swing will die out. The same for the pendulum. We can update the model with damping. So we have an initial damping factor. the damping is proportional to the velocity. So the higher the velocity, actually, the higher the damping factor, the contribution from the damping. So a slight modification. The purpose of this exercise is to verify that the model will indeed lead to a decaying pendulum. So one can do then the opposite. One can, and that's then the next exercise. One could essentially, here we have the negative, so the acceleration actually decreases. That's what the damping means. So run the code in the posted Jupyter notebook, make the plots, and verify the correctness. Here, the parameters are important. It may be, so the n determines the step size. So it may be that higher step size is higher values for n are needed. But know that you need to see a damping. One can still have damping and forcing. So this is quite a realistic model now. So there is a periodic forcing term that is applied. There is an amplitude and the A, and that will keep the pendulum from moving. That will keep the pendulum moving, so it keeps the pendulum from coming to a rest. Same question as the previous exercise. Run verify. So now there is a, so the contents actually have to be carefully chosen here. So if the forcing amplitude is too hard, then you will see that the pi over 4 will actually increase. So there will be then an increase here. The same with the damping. So the damping constant and the forcing term, they are important in this model. All right, let us look at some more examples. And instead of, so in addition of verifying whether it works, can we say something more in general? And it will turn out that we can. And in the case of linear systems, the solution trajectories are actually quite predictable. Here is an example of an algebraic curve. I'm sorry, it's a plane curve. A plane curve that is given as is an exact parametric form and is the solution of an initial value problem. And it is a linear system because the matrix is independent of x and y. So the x and the y now correspond to the coordinates of the curve. So we have a plane curve. It's called a cardioid, and you will see immediately in the picture why that is. This is an example of a linear system. It's also a perfectly periodic system. So the time t ranges between 0 and 2 pi. So you can run your numerical solver on this. This is a very nice test problem. And it's different from, here you see the picture of the cardioid. What's the purpose of this exercise? Well, apply the modified Euler problem to this problem. Now, it is a numerical exercise. Make sure that your step size is small enough so that you see a computed, that the curve that you compute is actually what you would expect. Here is another curve. So I don't tell you what it is. So, well, I can tell you it is a rose with 3 stems, with 3 leaves. So you will see that rose coming up if you if you apply the modified Euler method. And this is again a numerical exercise. Find well enough value for the step size, or in other words, how many, what will be, so your step size will be 2 pi divided by n. So what is a good value for n? Good experiments. Can we say something in general? Well, yes, if we have a matrix, we know that its eigenvalues and eigenvectors are very important. So you realize here in this general format, again, the companion matrix. It's now tilted, so it's actually a transpose, but you will have the same eigenvalues, the same relationship. So one can see that with this differential equation, there is a natural polynomial that is associated to this. So if you have to solve a linear problem like that, you can solve this problem in great generality in the following way. You look at the solution of the homogeneous system, and that is entirely determined by the homogeneous, by the matrix A. And in a way, what the slide also suggests is that when we looked at the test equation, the general format of the solution can be written as an exponential times the initial condition. And we can generalize this. So instead of having one number for the initial condition, we have a vector. Instead of the exponential, we actually now have the exponential of a matrix. We have the Taylor expansion of this matrix. And you recognize that we are taking powers of matrices. Kind of interesting again, we've seen the power method and the QR algorithm in our third project. For the third project, we had our Schur decomposition because we were working with symmetric matrices and real eigenvalues. But the Schur decomposition is actually a simpler form of what we call in general spectral decomposition. It's more general because we have now eigenvalues that can be complex, but the eigenvalues, it's still not quite completely general. We assume that they will be distinct from each other. Otherwise, we have the Jordan canonical form. And for this course, the Jordan canonical form, we do not touch. But what the spectral decomposition buys us is a diagonalization of the matrix, where the big lambda stores all the eigenvalues, and the matrix of eigenvectors is stored as this capital V. So if we compute our exponential, what we actually do is computing powers of our matrix, and multiple orthogonal matrices by themselves doesn't really change much. So what we actually are doing is that we are taking powers of the eigenvalues. And then you see what actually is happening. We can then write the general solution in terms of the eigenvalues and the eigenvectors. So the general solution with the decomposition, so computing the matrix exponential is actually hard, but it's not so hard if you do this on paper, because the matrix exponential is now the exponential of the matrix of eigenvalues multiplied by x. And we can do a coordinate transformation using the basis of eigenvectors. So we transform our problem into a much simpler problem. So here we have no longer an A, we have a diagonal problem. So we have diagonalized our problem, and we can go back to the original coordinates to write down the general solution of the homogeneous form of the linear system. And if we look at this, we are seeing that we take exponentials, and the exponentials can be growing, they can be decaying, or they can be periodic. So the periodic nature occurs when we have complex eigenvalues. In particular, when you have a zero, so a complex number has a real part. The real part is going to determine whether we are growing or decaying. And one is the critical value to look at here. So positive or negative real parts. If the real part is zero, then the imaginary part, the non-zero imaginary part, will give the periodic nature of the solution. Let's look again at the cardioid. And look at the homogeneous form. If you compute the eigenvalues and the eigenvectors, is this indicating that the solution is periodic or not? So write down the general form of the solution, computing the eigenvalues of the eigenvectors. So we have done this already numerous times with the linear algebra module. All right, let's look into a nonlinear system. And this is another application or another generalization of the test equation. So now there is a story. We give other letters instead of y. We look at rabbits, and rabbits have an exponential growth rate if there are no foxes. So foxes need rabbits to survive. So without rabbits, so a decoupled model, the rabbit population grows exponentially and the fox population is decaying. So we have two constants, an A and a C. The growth rate of the rabbits is positive, the decay rate is negative. So written in this form, this is just another way of writing the test equation again, the two cases that we can have. How do we get to a nonlinear model? Well, the growth of the rabbits is corrected with the product of the number of rabbits with the number of foxes. So this correction term grows if the population size is growing. Now, what is important is that when a rabbit encounters a fox, it's typically ends badly for the rabbit. So we have a negative constant, a negative correction constant, and a positive correction for the fox. So the foxes benefit from the encounter. So this is an ecological model. It's one of the simplest non-trivial models, but we will use this just to reinforce how you can apply modified Euler's method to this problem. So also it's forcing here, so you can still force this, you cannot actually force this into a matrix form because there is a product of the two functions. So the functions, we will call them y1 and y2. So you have a nonlinear model here. So that's actually the main point. So what is a nonlinear model? Well, a nonlinear model is where you have products of the unknown functions. All right, the modified Euler method again, and I will spare you the code, but this is the critical slide how you get to the code. So the code is posted, which you will need for the last exercise. So to write down the program, we forget about rabbit and foxes, so their encounter will be gross anyway. So we will write new letters, y1 and y2, and we have two functions. I used capital letters because we still had the little f somewhere. And you see now the standard form of the system of first order differential equations. So important for Euler and modified Euler, they are working perfectly fine, linear or nonlinear. So their application only depends on whether you can evaluate a function that gives the right hand side. And we have recipes for that. So the f1 and the f2 are defined, well defined, if we have the parameters a, b, c, d. So we have the predictor and we have the corrector. So this is Euler's method again for the system. To run the simulation, we need numerical values. We need realistic values for the four constants, the growth rate, the decay rate, and then the correction coefficients. Observe the signs are important. We also need initial values for the populations. So these are parameters that are given by the model. The numerical parameters are the ones that concern us most. We have a time interval and a number of steps that we do. So that will determine the value for h. Well, okay, so look into why is that then correct? Here you see it's also an advertising for the modified Euler method. It's a simple method, but modified Euler method does quite well. You see now the population sizes of the predator, prey in green, predator in red. You see that their interactions as the prey grows, then also the predator species grows with some delay. Now, at some point, there are too many predators and the prey starts to decline. Then also the predator population starts to decline because there is starvation. When there are too fewer foxes, then the prey population, the rabbit population, starts to again increase. So there is this very nice balance that exists, and that is represented by this beautiful face portrait. So we started at 3, 2. You can actually see the 3, 2 here. So 3 for the prey, 2 for the predator, and there is a periodicity. So we, after a cycle, we obtain again, we return again to the same state. So just like a pendulum, just like clockwork. So this is a very nice benchmark problem for our numerical methods. By the way, you see that the blue is kind of jagged a little bit, and if you would zoom out, you will see that it's actually not the lines. It would need to be a very fine line. So there are errors creeping in already. So 2 questions. We can turn this into kind of a boundary value. What is now the precise periodicity for this model? in the phase portrait, we start at 3,2. When do we come back at 3,2? So play with this model a little bit. And then the computations all run very fast. But suppose that we really want to find the optimal value for the step size. We want to do the smallest number of steps, but still obtain the value 3,2 when we come back from our cycle, so that we have a nice plot.